Good morning to all of you, and welcome to this WISE seminar that we are organizing as a part of Women's International Day celebrations here at CNIO. We extend a special welcome to all of you who have come from outside the CNIO, among others, the CNIO Friends, our philanthropy program. Today, we have a speaker who represents very well the spirit of March 8th. Dr. Eleonora Viezzer, full professor of physics at the University of Sevilla. So thank you very much, Eleonora, for accepting our invitation. Eleonora is a doctor in physics by the Ludwig Maximilian University in Germany, and as full professor, she conducts her research in the field of nuclear fusion. She is the scientific coordinator of various experiments at different tokamars, which are devices that uses magnetic field to confine plasma. And over there, she leads large experimental teams with up to 50 scientists. She is also the responsible officer for the active spectroscopy diagnostic at Aztec's Upgrade, and one of 4 scientific leaders on the plasma regimes within the Eurofusion campaign. She is also co-founder and co-director of the Plasma Science and Fusion Technology Group at the University of Seville and co-PI of the Smart Tokamak. Eleonora has published more than 150 articles in top scientific journals and has received an ERC grant in 2018 and an ERC Consolidator grant in 2023. Her research work has been recognized with multiple awards, among others the Princesa de Girona Award in 2022, the BBVA Physics Award for Young Experimental Researchers in 2022, and Women to Follow in 2023. The title of her talk is Nuclear Fusion, Bringing the Sun Down on Earth, which we can't wait to hear. Eleonora, the stage is yours.
Well, thank you very much, Isabel, and thank you all for having me here. Especially many thanks to Directora Maria Blasco for the invitation. It's really a pleasure and an honor to be here, and I'm really impressed by the center. I have just had a very quick, brief expedition through the center, and I'm really looking forward to see also your laboratories. So for me, yeah, it's a pleasure to be here and talk about nuclear fusion, bringing the sun down on Earth. And let's see if I can, yeah. So with nuclear fusion, we aim to provide a solution to the global energy problem. As we can see in this night vision of the Earth, the energy demand is strongly associated to the development of society. As we hope and expect, the global energy demand will increase day by day, as also developing countries have more opportunities to increase their well-being. To date, we depend completely on fossil fuels, such as coal, gas, or oil. Here we can see now the different sources of electricity generation in the United States, the evolution from 2010. Let me see if I know how to, the evolution from 2010 and the predictions or expectations up to 2050. About 60% of the electricity is produced with fossil fuels, and of course not only in the US, in the whole world. Although renewables energies such as solar or wind allow us to reduce this dependency, even the most optimistic projections indicate a strong dependence on fossil fuels even after 2050 if we don't invest and develop new energy sources. Fossil fuels have, of course, allowed us to develop into the society that we currently are, with discoveries such as the steam engine or the combustion engine. But they're also the principal agent for global warming, natural disasters, and, as we have been living not only since 2 years, but in the whole last decades, geopolitical tensions. When we talk about global warming, we also need to keep in mind the carbon footprint. Here we can see how much grams per CO2 per kilowatt hours are produced in the European Union. We can see that the carbon footprint is minimal, so it's green, in countries like in France or in Scandinavia, while it's maximal here in orange or dark brown in Germany and in Poland. Despite having a privileged situation here in Spain, due to the long sunshine hours that we receive and also strong winds at the coasts, we still produce an important amount of CO2. So we are here in the medium range, approximately. Now, if we have a look at the main energy sources that we use in the national energy mix, we see that in Spain we mostly have gas, nuclear energy based on fission. So in fission we have heavy nuclei which break up into two, emitting energy. And we also use, of course, renewables such as wind, solar energy or hydraulic energy. However, we also know that both solar and wind energy depend on the weather conditions and also on the actual time. During the night, we don't have any sun. Multiple studies have shown that an energy mix should contain a baseload energy contribution that is independent of the weather conditions and that is stable. In Spain, this baseload energy is currently provided by gas, quite some amount of gas, and nuclear energy by fission reactors. If we have a look at, for example, our neighbor in France, we see that almost 70% come from the nuclear fission reactors. This means that if we want to seriously fight climate change, we need to develop a sustainable energy mix that includes a baseload energy contribution and also the renewable energy such as wind and solar. But it's important to keep in mind that this baseload energy needs to be independent of the weather conditions and needs to be stable. And we have to find these solutions urgently because the climate change is not stopping. It will not stop by itself. And nuclear fusion can provide this main baseload energy and will revolutionize our industry. As you can see here, nuclear fusion has the potential to replace fossil fuels within record time. It is expected that within 12 years we could replace the fossil fuels. So it's expected to be the industry of the century, providing an estimated gross domestic product of 5 to 6%. Now, what is nuclear fusion? We all dream of an unlimited source of energy, and this dream can become true with nuclear fusion. Nuclear fusion powers the universe and is the energy source of the stars and of our sun. In the sun, we fuse 564 tons of hydrogen into 560 tons of helium per second. And the mass difference between the initial hydrogen and the resulting helium, the photons, are emitted in energy, following the famous equation by Einstein that simply tells us that energy E equal mc squared. And this means that energy is equivalent to the mass. Now, on Earth, we use nuclear fusion based on deuterium and tritium. So deuterium and tritium are simply heavier forms of hydrogen, isotopes of hydrogen. So deuterium has a proton and a neutron, while tritium has a proton and two neutrons. The good thing, or the advantage, is that we have this fuel present in our Earth. Deuterium can be extracted from seawater, while tritium can be extracted from lithium, which is available in the Earth's crust for thousands of years. So when we fuse these two together, we create a new particle. We create a helium nucleus, and a neutron is emitted, and again, an energy. And in this case, we emit an energy of 17.6 mega electron volts. Now, mega electron volts, maybe, it's not so common to use in our daily life. So if we translate that into quantities that we are more familiar with the hydrogen atoms that fit into a spoon, into a small spoon, so 2.5 grams of DT fuel, we can produce the same amount of energy if we would fill up this auditorium with 28 tons of coal and burn it. The same amount. Or another example, now that I have here a bottle of water, which we also usually give, with the atoms of hydrogen that fit into this bottle of water, we can provide enough energy for a family of 4 people for their entire life, for 80 years. So with nuclear fusion, we can produce 10 to the 7 times more energy per gram compared to fossil fuels. And that's why we say that it's virtually unlimited, because we have enough fuel on Earth. And it is clean, because we do not produce long-lived radioactive waste. Nuclear fusion has the potential to meet the world energy demand. Why? Because it has such a high power density. Now let's have a look at the energy consumption of Madrid. In 2022, Madrid used approximately 12,000 gigawatt hours. Now, if we want to meet this demand with solar panels, we would have to cover the entire city center with solar panels. Imagine that. If we take a fusion power plant that fits into a factory building, we could meet the energy demands occupying much less space. And in terms of Madrid's energy consumption, we would need 3 of these fusion reactors to be able to provide the consumption that is needed in Madrid. But of course, now the question is, how can we do this? How can we confine a sun on the Earth? Because one of the major challenges is, of course, a sun is super, super hot. Yeah? And the other question is when. Let's first see the question, how do we do it? So to make fusion a reality on Earth, and in general in the universe, we need extremely high temperatures. And on the Earth, temperatures that are even higher than in the sun. In the core of the sun, we have about 50 million degrees Celsius. And at these high temperatures, matter reaches the 4th state, the plasma state. We all know the 3 states, solid, liquid, and gas. How do we achieve it? By increasing the temperatures. And if we increase the temperature even a bit more, we arrive at the plasma. And the plasma is an ionized gas where the particles with positive and negative charge can move around freely. And the plasma is present in our universe. 99% of the visible universe consists of plasma. And one example is, of course, our sun. It's a big plasma ball, and also this beautiful solar prominences, solar flares, are also examples of a plasma. Now, to make fusion a reality on Earth, we need to achieve, I already mentioned, temperatures that are even higher than in the sun. Why? Simply so that we can increase the probability to make fusion possible, because in the end, what we use are 2 particles with positive charge. And what happens with 2 particles with positive charge? The same if you have a magnet or 2 magnets. When you try to bring them together, if you put the positive pole and the positive pole, what will happen? They will repel. And the same happens in our plasma. So we want to bring together particles with positive charge. We have to bring them together. How do we do it? By increasing a bit the energy, increasing the temperatures. And on Earth, we need about 100 million degrees Celsius. And here we see the next challenge. We have really high temperatures. And there's no material that can withstand these high temperatures, because we have to confine the plasma ball inside a machine. And now, yes, we get a video because unfortunately the embedded one did not work. So how do we do it? We use magnetic fields. And I hope, yes, I can see it moving already. So we use magnetic fields. Here we take a property of our plasma because we have charged particles. This means that using magnetic fields, we can enclose the charged particles and they will follow the magnetic field lines as you can see here. Our particles with positive and negative charge will follow these field lines. And, well, in a cylinder with two ends, we will lose our particles. So what we do is we close it into a torus, into a donut, as you can see here. But still with this geometry, we still have important particle losses and energy losses. And that's basically because the arrangement of our magnetic field coils here, you see that the distance is larger here, so we can still lose particles and energy from that side. How do we solve this? How do we circumvent this? We try to create a special geometry of our magnetic field lines. Instead of having just a toroid, we have these helical magnetic field lines, similar to the geometry of a corkscrew to open the bottle of wine. So you want to wind the magnetic field lines to enclose our plasma particles. And now, if we could please go back to the presentation. Thank you. Okay, thank you. So, yeah, here, this should work, yes. So here you see an example of such a plasma inside the machine. So here, inside the machine, we produce an ultra-high vacuum to create the plasma. So here we achieve the 100 million degrees Celsius. The plasma is everywhere. What we see with our bare eye is actually the coldest part of the plasma, which we see here in this red and magenta colors. So we heat up the plasma with microwave systems, very similar to the microwaves that we have at home, or also high energy neutral beams. So high energy neutral beams meaning that we inject those particles into the plasma, and with the collisions, they transfer the energy to the plasma particles until we reach the 100 million degrees Celsius. So our plasma is floating in vacuum inside this machine, which is called the tokamak. So tokamak comes from Russian and simply means toroidal chamber with magnetic fields. So we have our plasma floating inside vacuum without touching the walls. And that's why it's also inherently safe. We have a vacuum, and if this vacuum breaks, the plasma discharge will simply stop. There will be no explosion or anything else. So it's inherently safe. And well, here, this example is from the ASTIC subgrid tokamak that Isabel already mentioned, where I did my PhD, which we will also see a little bit later. The next slide, yeah. So with this technology, with tokamaks, commercial fusion energy will be a reality in the coming years. Here we see the development of fusion power over the years with different concepts. I have presented the tokamak concept because our research is in magnetic confinement fusion in tokamaks, but there is of course also the possibility to use lasers and use inertial confinement fusion that you may have heard in this past month also a lot in the news from the United States. If we think of commercial fusion reactors, the tokamak concept is the most advanced concept, the most advanced technology so far. So to date, with a tokamak, we have achieved 70% of fusion power compared to the input power. So we are not yet there at the ignition point, meaning that we produce more energy than what we need to get the fusion reactions going. And this will be coming within the next step experiments. What I also want to mention here, if we compare the evolution of the tokamaks, it's actually also very similar to the evolution of Intel processors that we use for our computers. Oops. And with the new technology of high-temperature superconductors for fusion energy, high-temperature superconductors, of course, not new, because they have been employed in medicine. They have been employed, for example, in CERN, in Switzerland, for large-scale accelerators. But for fusion energy, they have not been employed yet. And this is currently being developed. And with this new technology, we will obtain this goal even faster. So the discovery of HTS, high-temperature superconducting materials, enables a faster, more compact, and cheaper way to obtain fusion energy. Here we see now a comparison of the two biggest projects that will reach similar levels of fusion powers. We see ITER here on the right, no, on the left, sorry, the left for you. ITER that is currently being built in the south of France, in Cadarache. And SPARC, the SPARC tokamak, which is currently being built at MIT in Boston. For a comparison, you also see the size of a person, here and here, highlighted with these two yellow circles. So the application of high-temperature superconductors allows us to build a reactor that produces the same amount of fusion power, energy, but with a much smaller size. Now, SPARC employs this HTS magnet to provide a high-field, compact, alternative path to fusion energy on a timescale of less than 5 years. It's a private-public enterprise that was born in 2018, and it's actually also the private initiative, Commonwealth Fusion Systems, started as a spin-off of MIT. And you may also have seen the news in El Confidencial from just this past weekend. It was published, where they have announced that the results of MIT were published in peer-reviewed journals. And so they're now published, and it looks very promising. I did not have time to read all 6 papers, but I read a few, and exciting times are indeed ahead. So yeah, we are all really looking forward in the fusion community to get this experiment started. But now I also want to tell you a little bit about ourselves, our experiment at the University of Seville. So in Seville, we follow a similar strategy. However, here we want to employ a spherical tokamak design. And I will show you in the next slide what is a spherical tokamak design. Because here we can use the magnetic field more efficiently, and this allows us to build fusion reactors, again, more compact, smaller, and efficient in terms of power output and also costs. But what is a spherical tokamak? Here we see the difference. So the video that you have seen, and ITER, for example, also SPARC, these are conventional tokamaks. They all look like they have a donut shape. Spherical tokamaks, on the other hand, they work the same way as a conventional tokamak, simply the shape changes. We have a slightly different geometry, and here we use a spherical geometry that looks more like an apple. And spherical tokamaks are much more efficient compared to conventional ones because for a given magnetic field, we can achieve higher plasma pressures, about 40% higher. And higher plasma pressures, in the end, also means higher fusion power. So if we increase the pressure, we increase also the fusion power because we see here the dependence. So with spherical tokamaks, we can achieve higher plasma pressures at lower aspect ratio, at lower size of the machine, and this gives us a higher power output and also more cost efficiency, allowing at the same time for smaller and more compact designs. And we see this also in this figure of merit, where we plot the fusion power normalized to the input power, so the fusion gain. In the end, we want to be above 1. And ITER, for example, as a reference, has the target of Q equal 10, meaning that we want to produce 10 times more energy than the energy that we consume, or the power that we consume. So if we have a look at the Q equals 10, the ITER reference, and we go now down here to the spherical tokamaks, what we see is that we arrive here at a much smaller device. Instead of having 5 meters, we have here 2 meters in size. So spherical tokamaks allows us to reduce the size of the machine. if we combine this now with high-temperature superconductors, we can increase the magnetic field, meaning at the same time achieve higher fusion power. So with high-temperature superconductors, we can achieve higher current densities and therefore higher magnetic fields. And this again, so here we increase now magnetic field, we increase the fusion power, and this also allows us to reduce again the size and the costs of the machine, because high-temperature superconductors also, because they have higher operation temperatures, this implies that we have lower cooling costs. So compared to low-temperature superconductors, if we compare here this curve at 10 centimeters with the high-temperature superconductors at 10 centimeters, you can see that the window of operation increases in the magnetic field quite substantially. So with HTS, we can increase the magnetic field, and with spherical tokamaks, we can reduce the size. And in addition, we want to combine these two technology with a third one, namely with negative triangularity, which I will show you on the next slide. And negative triangularity allows us to minimize the interaction between the plasma and the wall that confines the plasma. When we minimize this, this allows us to maximize the reactor lifetime and also facilitates the integration of the magnetic coil system here, the neutron shielding, and also the tritium breeding blankets here at the central stack in the center of the device. Now, negative triangularity emerges as a potential game changer in nuclear fusion because it combines high fusion performance with a power handling solution. So standard tokamaks, like ITER that we have seen, use the positive triangularity shape that we see here. So here, this looks like a standard D from Dora, a standard D shape. But what we have seen is, in experiments, when we mirror this plasma shape and invert the design to an inverted D, to negative triangularity, we have found several attractive characteristics. So negative triangularity plasmas feature lower fluctuation levels, as we can see here, compared to the positive triangularity part. And if we have lower fluctuations, this also means that we have less losses of particles and energy. And at the same time, we decrease the fluctuation level, but still have high confinement, high efficiency of the plasma. And in addition, negative triangularities also feature a larger divertor wetted area, meaning, as we can see here, that we can increase the area where the plasma is in contact with the wall, because on these lines, the plasma will be in direct contact with, in this case, it's called the divertor. It's the lower part of the device. And this is very beneficial for the power exhaust of the plasma. So these three technologies combined allow us to provide a unique global solution to offer the most compact and economic fusion reactor. And in our fusion to grid strategy, in the horizon of this strategy, the spherical tokamak SMART that we have built, designed, and are currently commissioning at the University of Seville is the first step. So SMART will be equipped with copper coils, and it's worldwide unique because it's the first spherical tokamak that has the capability to operate with this negative, with this inverse D triangularity shape. It's also the first Spanish spherical tokamak, and unique because it has the possibility to have flexible shaping, so we can do both negative triangularity, the inverse D, and also positive triangularity, the standard D, and compare our results also to other tokamaks. And here you see a picture now of the device from early this year, where we have built all the components now together, and we're now in the commissioning phase to get this device started. We actually had the first plasma. This was very exciting. The first plasma we had beginning of this year, a glow discharge heated with microwaves. So you see here the actual plasma we can see with the bare eye. And so the next steps are now to commission also the magnetic coil system and then to have demagnetized plasma. The next step on our horizon is H-smart, where we want to achieve for the first time fusion temperatures in a spherical tokamak with negative triangularity. And here we also plan to have a test bed for these high temperature superconductor magnets, because our goal is to have, remember, these three technologies combined. And these three technologies combined, we aim for E-smart. So in E-smart, our main goal is to produce more than 100 megawatts of net energy with a positive energy balance. So with a fusion gauge of Q larger than 1. And to achieve that in the world's most compact and most efficient machine. And the team behind this strategy is the Plasma Science and Fusion Technology Laboratory. You see here a picture of our team from earlier this year when we had the inauguration of the tokamak. We are a strong, experienced team, worldwide leading in many aspects of fusion science, with more than 20 years of experience in instrumentation, operation, and modeling of fusion reactors and all the associated systems. The core of the team consists of 30 full-time researchers and 25 partial-time researchers. We're a mix of physicists and engineers, and we also have very strong ties to the private sector. We're collaborating with many institutions around the world, basically with all major magnetic confinement fusion devices. And one of our biggest collaborators is the Max Planck Institute in Garching, Max Planck Institute for Plasma Physics in Garching in Germany, which hosts the Astex upgrade tokamak. And here Isabel already mentioned. Here basically I was born scientifically, so to say. I did my master thesis and my PhD thesis there. And here you see a picture from, yes, that's me, about 14 years ago now, when I started my PhD. And I got a phone call from the secretary of my academic advisor, and she called me and told me, Ellie, please go down. Your supervisor selected you for an outreach project. She didn't say more. And I said, okay, well, then I go to this tokamak hall, and then I see myself with 3 other students, with a team of 10 or 15 people with cameras, and what they wanted to do in the end was a 3D virtual panoramic tour. Yeah, with pictures, with videos. And this is one of the pictures that the photographer took, and he even won an international photography prize with that. It shows you how we work inside. Our machine is not pink, yeah, so it's an artistic view. But we are dressed like this, that is true. And I show you a more realistic picture of how the machine looks like. So you see here all the coil systems and the walls made of, in this case, of tungsten. And this is a picture from a few members of our team when we traveled to Germany to calibrate and characterize our diagnostics once the machine is open. Of course, when we have the plasma discharges, there's no one inside. Yeah? And yeah, just to finish up, I just want to tell you a little bit about myself and how I ended up in fusion, especially given that we had the 8th of March just a few days ago, and also given that we are all researchers, the 11th of February, which is also a very important day. So how did I end up in fusion? My background is actually a mix. You can probably hear that I am not from Spain. So I am half Italian and half Philippine. And I grew up between Italy and Austria. So between 2 countries that are not very similar, because I would say Italy is very similar to Spain. And Austria is, although they are neighbors, but it's quite a different country. And there I saw also for the first time snow, which is of course exciting, being a 6-year-old child when you move there. And in Innsbruck, in Austria, I did my school there, I did my high school. And my physics teacher was actually decisive for me to study physics, to take the decision to study physics. So my physics teacher, she recommended me and a very good friend of mine to go to a winter school at the University of Innsbruck in our last year in a bachillerato, in our last year before we graduate from high school. Back then I wasn't yet so sure. So at the age of 14, 15, I wanted to become a medical doctor. And then I did an internship in a nursery, in a nursery, and I got in touch for the first time with blood. And I just panicked. I could not see blood. I said, okay, I can't do this. I can't be a nurse or a medical doctor without, this is incredible. And then I said, okay, I have to change my mind. And then at the age of 15, 16, I didn't really know what to do. My family told me, Ellie, now you speak so many languages. Maybe, you could work, for, I don't know, for international schools, or think about it. And I was thinking, but having multiple languages is something that my parents gave me. And it was their present. And it's already something that I know. And I found it a little bit boring. So I thought, no, I actually want to do something else. And I always liked physics and math and biology and chemistry at high school. I really liked the experiments. I really liked our chemistry professor, for example. He always wore a white bata. I don't even know the name in English now. And I always want to have a white bata as well. So my physics teacher, in the end, she told us, well, go to this winter school and just have a look. And in this winter school, the groups at the university, they showed us their experiments, their daily life as a researcher. And it was so fascinating that in the end, this week, where in principle we had vacations as a student, as pupils, we had vacations. But this was so decisive that in the end, both of us decided to study physics and math. And here I brought you a picture, not when we were 18, but from 2018, when we met again after a couple of years without seeing each other. We met again in Brussels. And in Brussels, we met for the interviews of the ERC starting grants. So that was really a coincidence. We both were lucky and also got it. And since then, also are in touch every day and to talk about anything. Anyway, so I studied physics and math at the University in Innsbruck. And after 2 years, at the age of 19, I decided to move to Munich. Simply because the University of Innsbruck was nice. They were really pioneers in quantum physics. But I was not so much interested in working with lasers and quantum bytes and mirrors, so I wanted to see something else. So I went to Munich, and there at the Ludwig Maximilian University, it was one course, plasma physics course, and that one was determining for my career. Because of course, back then I did not know what is a plasma. I learned about what is a plasma, what is nuclear fusion, and I really wanted to contribute in making a change in this world and working to find an alternative for an energy source. So in Munich, I finished my studies, I did my PhD. Here you see a picture with my family from the graduation day. And in 2016, I then moved to the University of Seville with a Juan de la Cierva grant and a Marie Curie grant. And in Seville, of course, I also met the new culture, a change also from Italy and Germany. And here, well, I have, of course, in Seville, I've also gotten to know Semana Santa, which is coming soon, and also Feria de Abril. And here I bring you a picture. And of course, well, in the University of Seville, we could establish our plasma science and fusion technology group in 2016. And since then, it has been growing. In the first year, we were 5. Now we are more than 30. In our last Christmas lunch, we were 33 members that attended, and we were missing 2 or 3. And yeah, we also set up the smart tokamak that you have seen, that I have talked a little bit about. And in the group, well, we also got 2 ERC grants, the starting grant and the consolidator grants. And this, I would really like to highlight that it's achieved as a group. It's given to one person, but there is, of course, a whole team behind that. And I think it's very important to acknowledge that. And Seville is also very important and very special to me because last year I became a mom of this little guy here, and he's actually also came to Madrid with me. He's now with abuela, with grandmother, getting to know all the parks in Madrid. So just to finish, I myself would have never believed that a small little girl like me, with this background from Innsbruck, from Italy, from the Philippines, from a little bit of chaos, could one day be on the same stage as the Spanish royal family. So nobody should put a limit to our dreams. I think we should all follow our dreams. And yeah, especially I think being a girl, a woman in science, it's important that no one tells us that we are limited in anything. So thank you very much. That's it from my side.
Thank you very much, Eleonora. Fascinating talk, fascinating technology, and fascinating career. I'm sure we have questions from the public.
Yes, please, questions. There's one maybe hand.
Eleonora, congratulations. I think your talk was fantastic. Your career, what you're doing is exciting. It looks like the future, right? I wanted to ask you, the funding for you have these ERCs. I imagine these are millions of euros, but which is the participation of the public funding from Spain? Do you find Spain is pushing, like you said, France is having one of these tokamaks in the south of France.
Yeah.
Then you have the MIT.
Yeah.
So Spain is going to be a player in this thanks to you and your team. I mean, which is your perception?
So yes, we will be, but it depends also on the funding of the public sector. So we have funding from Europe, of course, from not only the ERCs but also the Eurofusion Consortium, and we have funding from Junta de Andalucía, so from the local government, and with the Spanish ministry we are in contact because such an endeavor we cannot push ourselves, and we cannot push, I don't know, I mean, with 2, 3, 4 ERC grants, that's not possible. The seed funding for the smart tokamak came from the local government in Andalucía. And of course, this, together with the ERC grants, has attracted more funding. And we are also in discussion with the private sector, because in the end, I believe that it has to come from both. And I think it is a project that is of national and international interest. I didn't mention it here, but for example, in the smart tokamak, we have funding even from the US Department of Energy, together with the University of Princeton. So they got 5 million so that they can build their systems into our device. And this is also just the first step.
More questions?
I was curious, you said that in order to get tritium, you would need to extract lithium from the earth crust.
Yeah.
And so, ecologically speaking, like in terms of quantities that you would need to produce the raw material, what is the impact? Like in order to go in the mines, get all the lithium out, do all the production. I mean, I do understand the whole point is to get clean energy, but upstream to get the appropriate reactive, how ecological is the process of producing those reagents?
So we have, we are focusing on the deuterium and tritium reaction because it has the highest probability at relative low energies to get fusion energy going. And the quantities that we need to produce fusion is really small. So in the largest tokamak that was operating until December in JET in the United Kingdom, there we have a plasma of 80 cubic meters, plasma volume of 80 cubic meters, and what we need to produce the fusion reactions there is equivalent to a piece of hair, in atoms. So it's really little. But of course, we have to take into consideration that we have to extract lithium from the mines, and that we will need to produce the tritium out of there. In the future, there are also other reactions available that produce energy, however, at slightly higher reaction cross sections. So there we would need to find maybe alternatives, but this is ongoing. Yeah. Thank you.
Thank you very much. Fascinating. So I have many curiosities. So I have been hearing about fusion energy in 1 decade for 3 decades already.
Yes.
Right?
Yes.
So is this the good one?
This
the
is
first question. So the second question is, how much is the balance between the other strategy, the laser induced fusion?
yes.
And the third question is, how do you see actually the energy when produced coming to people for free? Or because, of course, there's a lot of economic interest on all this. So it sounds great on paper, but I guess all these things would be patented, and then people may get cheaper energy, but not free energy, right? So that's
Yes.
what I would like to
Yes.
hear your opinion about. Thank you.
Yes, thank you for the 3 questions. Let's see if I hope I won't forget anyone. Maybe let's start from the last one. Of course, you're right, and we have to think about that. And especially given that there are many private companies now coming up, promising different concept alternatives. The tokamak concept that I presented today is the most advanced one. It's the most advanced one, and it's close to the ignition. And here we have public and private companies working together. So the ITER project, for example, I mean, it's situated in France, but it's an international project. And there we have researchers from all the world coming together, working together to make fusion energy available for humankind, not just for one country. And of course, this we have to take into account. We have to take into account that now that there is more interest from the private sector, that we don't enter into a loop where every country or every company just works for themselves. So far, with the companies that we have been working, like Commonwealth Fusion Systems, it's an open two-way interaction. Yeah, but of course, this has to be taken into account. Then the second question, I think, was the comparison to the laser technology. Yes, so of course, within the laser technology and inertial confinement fusion, we have achieved, you have heard it, in December 2022, they have reached for the first time a fusion gain of 1.5, larger than 1, which is, I mean, that's amazing. That's great news. Yeah, but of course we have to take into account also the technology of lasers at the current stage. We have achieved this for hundreds of milliseconds. Yeah, this is not something that within a few years we can have a steady state solution. We have, of course, to work also on laser technologies and see how we can increase that, increase the confinement times. Because in the end, if we want to have a fusion reactor, we want to have it going 24/7. Yeah. And so again, here, tokamaks are more advanced in the end. And then regarding the first comment, now I remember that you've been hearing since 3 decades, sorry, that in 1 decade it will be there. Actually, I've heard it even worse, that it always takes 50 years so that fusion will be there. I mean, this was maybe true 50 years ago. Yeah. 50 years ago, 1970, where we started off. But look at the evolution that we have experienced. And most of that coming only from the public sector. And the public sector is tough. Yeah, it's really tough. And ITER is mostly also coming from the public sector. And it's a really big device. Of course, it takes years to be built. But there's interest now also from the private companies, and I think it's great that there is interest, because it shows us, and it also shows the society, that we're not 50 years away. Our technology is mature, and there are different concepts, and I believe we have to invest in the different concepts, and stay tuned for the next couple of years. Yes.
Hello, and thank you for the talk. It has been fantastic. I am curious about how was your arrival to a field which was already very well established and a large community, which had a lot of years, had been going for a lot of years, and you get there being young, I assume, with new ideas. How was it? Was it difficult? Did you find challenges? Or that's one question. And the other question is, what are your? How is it to lead such a diverse and large team, also with international connections and in a big project?
Yeah. Thank you for the question. So when I started at Infusion, I was like I am still like a sponge, I think. So I started with an internship at the Max Planck Institute, and basically what I did in the plasma physics course, I asked the professor if I could do an internship with him, and he said, "Well, sure, just come one day to my office." And the office was not in Munich; it was in Garching, so it was like half an hour with a metro, and I was super excited. And I did my internship there with another professor, and the environment was super inclusive. It was already, I came from a classroom directly into an environment with international researchers. There also, everyone, it was in Germany, but everyone spoke in English because there were people from everywhere around the world. And some only spoke in German, okay, but and I was so fascinated that I asked, I think 1 week later, if it was possible to do my master thesis. And he said, yes. I got introduced to another supervisor. And when I was younger, I always thought of, okay, what will I do in the next couple of months? I was not thinking, oh, will I do a PhD? I did not even know what is a PhD when I finished my studies. I did not really know what is research. I got to know it during my internship and the master thesis. And I really, really liked it. And so then I decided to do my PhD. And not everything everything was great. Of course, I also experienced challenges. I experienced, being a young student. I remember that when I was at different lectures, also doing my PhD, they always told you, you will be the ITER generation. You will see ITER going, and yes, I still think I am the ITER generation, but now it's been 14 years and there's still no plasma. So that was a little bit, but it's still exciting, because it's such a big device, and I think it's important to not lose the goal that you once had. So for me, even having challenges, and maybe also having challenges because I am a woman and I am still a young woman, it was challenging, of course. And especially in physics, here it's so great to see so many women in this auditorium. In physics, we are like 10%. I was in lectures, I was the only girl, and I did not realize it. I was in seminars, I was the only girl, and I didn't realize it. And just because of my friend next to it next to me told me, Ellie, afterwards, Ellie, did you notice that you were the only woman? I was like, no, but now that you tell me, thank you. Yes, now I realized it. So we have to work a lot on that with women in science, especially in physics. It has been changing, but there is still a lot to do. And regarding the second question of how to deal with a large international team, I think diversity is super important, and it's so important. And I have been seeing this not only with our group in Seville, where of course we when we started, I mean, I was the only one from abroad, but I was just one of them. Yeah, I was just one of them, and with my back then broken Spanish, and it has improved a little bit since then. But I've also noticed how important it is to have more internationals in the group, so that our students also feel comfortable, for example, talking in English. I remember that the first students, they had good level of English, but they were just too shy to speak in English. And at some point we decided, okay, let's do our group meetings in English, even though I could speak Spanish and but we wanted that it's easier also for the students once they go, for example, to Germany to do some experiments, that the transition is easier. And so I think diversity is super important in all aspects, not just gender aspects, in all aspects. And
so, Elena, as a scientist, you focus on building these devices, but for the society, at least to me, what transpires is that, in Europe, we have always been very cautious. I mean, France is the exception, right? But you hear the news where, China had a plan to build 20 nuclear reactors, and then France some others, but Europe was always, lagging behind. So what about this news? I mean, do you feel that with these new reactors, they might be opening up to investing more strategically as a continent?
Yes, Europe is changing. Europe is changing and is investing also. There is a plan from the European Commission exactly dedicated to the collaboration between public and private enterprises for nuclear fusion energy. So in Europe, there is a change. And there are also private companies coming up, and many companies coming up. The most prominent ones, and also the first ones in Europe, well, the United Kingdom, they're not part anymore of the EU, but still I consider them being in Europe. Tokamak Energy, and there are many more. So in Germany and in France, as you have mentioned already. So it is changing. Of course, compared to the US, yes, the US is the continent of the American dream, but we are not lagging behind. And here in Europe, we have our ideas. And I think it's important that we invest also in our ideas, and that we try to keep, and I think this is true for any aspect in science, that we try to keep the talent here, the talent that we have already here and that is doing the PhD here, but that we also keep the talent here.
Yeah, I'm not worried about the talent. It's more, the talent is clear, the technique is clear, the methods are clear, but the political aspect of it and the bureaucracy,
yes,
we win them by miles. And I don't know to what extent that affects also in which, but they might agree to go ahead, but in the end, will they really invest massively in building these things? Or
we hope that yes. I mean, of course, you're right that we can, of course, start a political debate. In politics, the timelines are always thought in 4 years. And in 4 years, to change something is really difficult in any aspect. So I do hope that we have we have these opportunities, that we get these opportunities. I mean, we are in contact with the local government in Andalusia and also here with the Ministry of Science. So hopefully in Spain, starting now from Spain, we can have, we can provoke this change.
One question. So, for instance, tokamak energy in the UK, you mentioned. How far is it from selling this energy? And once it's available, how it would compare in price to other types of energy?
Yes. So in the UK, they are working also in tokamak energy. They are working on the spherical tokamak design combined with high temperature superconductors. So it's also similar to our strategy, but not with the negative triangularity. And they are now building a new machine. They had ST40, where they have reached fusion temperatures. And the next step is ST80, where they want to increase the magnetic fields. So we are not there yet, also in the UK. How will it be competitive in the market? I think this is something that we need to see and we need to experience. Who will be the first one? And who this I cannot tell you. This we have to see. And yes, but I hope that with our strategy, we will belong to those.
Okay, I think we are gonna finish here because we are a little bit over the time.
Sorry.
If you want to, no. It was a pleasure to listen to you. But we have also now a small snack outside. So if any questions, if you want to ask her any questions, you can also do it outside. Thank you very much for this fantastic talk. Thank you for your interest, and see you in the next WISE seminar.
Thank you very much for having me here. Thank you.